Hi, this video is about a 3D rendering engine. This rendering engine has several features. For example, that it can render objects with Gouraud shading, also called per vertex shading, or Fonk shading, also called as per fragment shading or per pixel shading, or even with NPR, that is non-photorealistic rendering. The processed materials may be diffuse plus Fonk beam type specular surfaces. The engine can handle textures. There is going to be a class that can produce chessboard-like procedural textures, and there is a complete zoo of different parametric surfaces, including spheres, trocticoids, toruses, Möbius strips, Klein bottles, Boy's surfaces or Diniz surfaces. The first class of this engine is implementation of dual numbers. Recall that dual numbers are friends or sisters or brothers of complex numbers. The implementation of the basic operations like addition, subtraction, multiplication, and division are similar to those of complex numbers. However, there are differences. In case of a complex number, the square of the imaginary unit is equal to -1 by definition. Here, in the case of dual numbers, the square of the imaginary unit is 0. In this way, we can guarantee that the arithmetic rules of dual numbers are identical to the arithmetic rules of derivatives. So if we replace a formula or a program using floats, for example, by data types of this dual number, then the result not only available for the formula, but also for the derivatives. In addition to implementing the 4 basic operations, addition, subtraction, multiplication, and division of functions, we also make our implementation prepared for standard mathematical functions like exponential, sine, cosine, tangent, etc. and generalize these implementations in a way that they can also handle expressions with the application of the chain law. This general implementation is a template because when we have a function, we might have more than one derivative. In fact, parametric surfaces are going to be two-variate functions. Therefore, parameterization type T will be vec2 that is able to represent two derivative values. In order to use a shorthand notation, we will denote dual numbers with two derivatives by dnum2. The next class or structure is the virtual camera, which is defined by external parameters specifying the location of the camera in WI, the point where the camera looks at by W look at, and the so-called preferred up direction of the camera or the preferred vertical direction of the camera. We are calling it preferred because the algorithm will automatically take care of checking whether this vector is orthogonal to the optical axis of the camera, and if it is not, only that component is used from this preferred up direction, which is really orthogonal to the optical axis. The optical axis is in between the eye and the look at points. The other group of parameters of the camera are called intrinsic or internal parameters, including the vertical field of view, aspect ratio, and the front and back clipping distances. In the constructor of the camera, these intrinsic parameters are set. During the application of this camera, in an object-oriented program, we usually need two functions. The view or V transformation, which takes the world, including the camera as well, and translates and rotates everything in a way that after applying this transformation, our camera will be in the origin of the coordinate system, and its optical axis will be the same as axis Z or minus Z, and its vertical direction will be axis Y. In the implementation of this view transformation, the corresponding transformation matrix is computed from the extrinsic parameters. The second transformation associated with a camera is the projection transformation that distorts the space again in a way that after applying this transformation matrix, the view frustum will be a cube of corner points -1, -1, -1, and +1, +1, +1. In other words, this projection transformation will take the origin, the position of the camera before the application of this projection transformation, to infinity at the end of axis Z. So the application of this projection transformation replaces perspective projection by a much simpler orthogonal projection. Well, in our three-dimensional rendering engine, we are going to support rough surfaces that can be described by the diffuse reflectivity, specular reflectivity, ambient reflectivity, and the shininess that specifies how polished the surface is. The diffuse, specular, and ambient reflectivities are spectra. That's why we use this Vec3 type to represent them, because they may have a different scalar value on different wavelengths, and we use the wavelengths of red, green, and blue. Light sources are defined by their normal emission, LE, and an additional special emission called the ambient light. So every light source may have its own ambient light. Additionally, the normal light source has a position which is of type Vec4, so we specify this position with homogeneous coordinates. The application of homogeneous coordinates allows us to specify even points at infinity. So this single structure can handle both positional light sources, where the light source is at a finite distance, or even directional light sources, which can be imagined as a positional light source being infinitely far. The checkerboard texture is a texture, and in its constructor it generates an image that will be used as a texture. The algorithm is very simple. It creates a checkerboard of columns and rows specified by the input parameters, and the two cells will be colored with yellow and blue. Render state is a kind of communicator object between geometric objects and shaders. Recall that the actual parameters of rendering are stored in the geometric objects. However, these parameters must be transferred as uniform parameters of the shaders. So the real question is whether these parameters belong to the geometric objects or to the shader. So in order to resolve this problem, we introduce this render state, which can be filled up by geometric objects depending on their internal parameters, and the shaders will use the information stored in this render state, and only that part of the render state will be fetched which could be used in a uniform parameter of a particular shader. Our shader is a GPU program. A GPU program can handle shader programs written in GLSL language. The GPU program compiles them, links them, and makes them active and forces them to run on the GPU. So in addition to these general features, our shader just add two functions that initializes the material properties and light source properties as uniform variables. We have three different particular shaders. The Garrod shader or vertex shader evaluates the illumination formula for the vertices of the tessellated geometry. The evaluated color or radiance information is interpolated for internal pixels by the hardware. So the vertex shader program looks like this. it gets uniform parameters describing the transformation matrices, material properties, and also the light sources. So transformation matrices include the model view projection transformation, modeling transformation, and the inverse of the modeling transformation. We allow at most 8 light sources, and of course we have to specify how many light sources are active from the 8 available light sources. The illumination also needs the viewing direction, which can be computed from the world position of the camera, called WI, and this material uniform variable stores the material properties like the ambient diffuse or specular reflectivities. As varying inputs, this shader gets the position of the vertex in modeling space and also the surface normal of the original surface at the point of the specified vertices. The main task of the vertex shader is to transform the input point to normalized device space, which happens usually with the application of the model view projection transformation matrix, and we get the result in homogeneous coordinate, and the result is supposed to be written into the GL position output register, because the fixed hardware assumes that the point will be written into this register and is interpreted as normalized device space coordinates. The remaining part of the vertex shader is responsible for the calculation of the output radiance, that is the color, the reflected color of the surface at that particular point. In order to do that, the point and the normal vector are transformed to world space, because the virtual world is the environment when points can meet light sources and the camera, so we are able to obtain the view, light, and normal vectors in the same coordinate system. First, the point is transformed from modeling space to world space with the application of the modeling transformation matrix. If this is available in world space, then the viewing direction is just the difference between the eye position and the Cartesian coordinates of the transformed point. These Cartesian coordinates could be computed with homogeneous division, that is, taking the first 3 coordinates of W position and dividing it with the force value. However, looking at this line, we do not really see that computation. Instead, we see that this vector, this difference vector, is multiplied by the W position variable's force homogeneous coordinate. So why is that? In theory, it can happen that this transformation matrix, or the application of this transformation matrix, ends up in a point that is infinitely far, so its force homogeneous coordinate is equal to 0. Obviously, it's strictly forbidden to divide by 0, so that's why we multiplied both factors by this value. The good news is that after this multiplication, the result will be valid, even if the force homogeneous coordinate is 0. If the force homogeneous coordinate is not 0, we have the freedom to multiply both factors by a scalar, because we will normalize the result anyway. Any scalar multiplication factor will be eliminated by normalization. The normalized function returns the viewing direction. Then we compute the normal vector in world coordinates. The normal vector in modeling coordinates is here, and we know that if points are transformed with a homogeneous linear transformation M, then when normal vectors are transformed, the inverse of the same matrix should be used, and while points are considered as row vectors, normal vectors must be considered as column vectors. The force homogeneous coordinate doesn't make any difference if this is an affine transformation, so if it doesn't make any difference, we say that it's 0. This is just an extra thing here. Recall that when we develop the illumination formulae, we usually assume that the normal vector points into a similar direction than the viewing direction. We check whether the normal vector and the view direction point roughly in the same direction, because if it is not the case, we should flip the normal vector. Then radiance is initialized to 0 and we visit light sources one by one. For a particular light source, we compute the illumination direction. Recall that we use the same trick as before, because light source positions can also be at ideal points that are infinitely far, because we handle directional light sources and positional light sources uniformly. As before, we multiply the two Cartesian triplets with the fourth homogeneous coordinates before computing the difference. And again, this doesn't modify the result if the fourth homogeneous coordinates are non-zero, because we normalize the result anyway. However, when the fourth homogeneous coordinates are 0, we still get a valid result. Having the illumination direction and the viewing direction computed in here, we can compute the halfway direction and then evaluate the illumination formula for rough surfaces, which means that the reflected radiance due to a particular light source is the ambient light contribution, which is just the product of the ambient reflectivity and the ambient light intensity, and this product is computed independently on the wavelengths of red, green and blue. Then we add the diffuse term according to the Lambert's cosine law, which is the diffuse reflectivity multiplied by the cosine theta. Theta is the angle between the normal vector and the illumination direction. And if this angle is greater than 90 degrees, it means that the object occludes the light source. The possibly negative value of the dot product must be replaced by 0. Finally, we add the specular component, which is the specular reflectivity, and the cosine delta to the shininess power, where cosine delta is the angle between the normal vector and the halfway vector. And again, we replace any negative value in the dot product by 0. The diffuse and specular components are proportional to the real emission intensity, which is also a spectrum. So it must be computed independently on the wavelengths of red, green and blue. The output of the vertex shader is the radiance output variable, which goes through the fixed pipeline elements and interpolated for every pixel that is covered by the rendered primitive. So when we arrive at the pixel shader, the interpolated radiance will be in the input register, and this interpolated radiance is just copied to the output register that is written into the frame buffer. So the fragment shader in case of pair vertex shading is very simple. It is just a direct copying. The bind function of this shader is responsible for initializing the uniform variables based on the content of the render state. So the render state is a huge collection of transformation lights and camera parameters, and here the shader can decide which particular parameter are used to initialize the already known uniform parameters of the GPU shaders. Our second shader is the Phong shader, also called per fragment or per pixel shader, because here the illumination formula is evaluated for every pixel in the vertex shader. So on the level of triangles or vertices, only the vectors needed for the illumination computation are prepared. And these vectors are interpolated by the fixed function elements when vertices go through these elements and finally they arrive at the pixel level. Concerning the vertex shader, it has uniform parameters again, but these uniform parameters are used only to compute the vectors needed for illumination, including the normal vector, illumination directions for every light source, and the viewing direction. In the varying input of the vertex shader, this vertex shader gets the position of the shaded vertex, the associated normal vector, and we also prepare for texturing, so we pass the UV or texture coordinates with the vertex as well. The outputs of the vertex shader are the vectors needed by the illumination formula, the normal vector, the view direction, and up to 8 illumination directions. There is an additional output value, which is the UV or the texture coordinate, which will also be interpolated by the hardware. The vertex shader computes these output variables based on the transformation matrices and the content of the input registers, the vertex properties. So first of all, the point from modeling space is transformed to normalized device space and written into the output register called GL position. Then the point is also transformed to world coordinates because illumination is evaluated in world space. For every light source, we compute the illumination direction here, and again we use the same trick of multiplying both three-dimensional vectors specified in Cartesian coordinates by the fourth homogeneous coordinates in order to handle infinitely far directional light sources and positional light sources uniformly with the same formula. The view direction is just the difference of the eye and the point in world coordinates, and again we use the trick of multiplying both vectors by the fourth homogeneous coordinate of the world space position. The normal vector in world space is obtained by transforming the normal vector in modeling space to world space with the application of the inverse modeling transformation. The texture coordinates are just copied without any modification. The vectors, as well as the texture coordinates, go with the point through rasterization, and finally the process arrives at the pixels where the output registers or the contents of these output registers are interpolated, and this fragment shader gets the interpolated values that are valid for that particular pixel which is shaded right now. As always, the fragment shader's responsibility is to compute the output color or the output radiance associated with this pixel. The normal vector, view vector are normalized, so we get the normal vector in world space, the viewing direction V in world space. Again, we check whether we see the front face or the back face of the same polygon, and if we see the back face, the normal vector is just flipped in order to keep the validity of the illumination formula, which is assuming that we see the front face of the polygon. The texture color is obtained by fetching the texture map via a sampling unit. The sampling unit is identified by this diffuse texture, and it's a uniform variable. The ambient and diffuse reflectivities are modulated by the texture color. So again, the task is to compute the reflected radiance, so we consider all light sources one by one, compute the illumination direction, and then the unit half-way vector. In both cases we have to apply normalization to make sure that these are really unit vectors. Cosine theta is just the cosine of the angle between the normal vector and the illumination direction. Should it be a negative value, we replace it by 0, and cosine delta is the cosine of the angle between the normal vector and the halfway direction, and again if it is negative we replace it by 0. Finally, we apply the illumination formula. This is the ambient light contribution. This is together with the emission intensity, the Lambert's cosine law, the diffuse light or illumination contribution, and finally this term is the specular term according to the von Blin formula. And the computed radiance, taking into account all light sources, is written to the output register which goes to the frame buffer. This shader also has a bind function that initializes the uniform parameters of this particular shader based on the content of the render state. Our third shader is the non-photorealistic rendering shader, which provides a kind of artistic look. It simulates the process of painting or drawing. Actually, the vertex shader of this MPR shader is very similar to the vertex shader of Phong shading. So we just compute the output registers and output texture coordinates based on the varying inputs and using, of course, the transformation matrices, light source or camera positions or eye positions available in uniform variables. The algorithm is the same as we have seen before. The difference is in the fragment shader. So in the fragment shader, as in the case of the Phong shader, we get the interpolated normal view or illumination directions, and we compute a quantized diffuse reflection formula to simulate that a painter doesn't have infinitely many different colors, so he has to choose from finite number of colors, therefore we have some kind of quantized image. And additionally, painters like to draw the silhouettes of objects with black, and we also mimic that process in our shader. So let's see. First of all, the normal vector view direction and illumination directions are normalized. Again, we check whether we see the front face or the back face, and if it's a back face, the normal vector is flipped. The Lambert's law uses the cosine of the angle between the illumination direction and the normal vector. This cosine is quantized, which means that we check whether this cosine is bigger than 0.5 or smaller than that, and then the two cases are identified by two numbers, 1 and 0.5 respectively. So if the illumination or the cosine delta is big enough, we use the high intensity color, and if it is lower than 0.5, we use the low intensity color of the same hue. Additionally, we check whether this pixel belongs to a silhouette or not. A silhouette separates front faces from back faces. So a silhouette can be recognized from the fact that here the normal vector is perpendicular to the viewing direction. We check it with the threshold, so if the cosine of the angle between the normal vector and the view direction is close to 0, which means that we are about the orthogonal case, then the pixel color is replaced by black. Otherwise, we use the quantized textured diffuse reflection and write out the result to the frame buffer. The bind function initializes the uniform parameters of this particular shader. Okay, the next task is the definition of the geometry on the GPU. We know that this is encoded in vertex array objects, and a vertex array object can have multiple vertex buffer objects. And vertex buffer objects store the locations, normal vectors, and texture coordinates of the vertices. So in the constructor of the geometry, a vertex array object identifier is asked, and we immediately bind this vertex array object identifier because very probably we are going to initialize it after constructing it. Inside this vertex array object, one vertex buffer object identifier is created, and we bind that vertex buffer object because, as I said, we hope that we are going to initialize it right away. Of course, On this level, we do not know how to draw the geometry. On this level, the draw function is just a pure virtual function. If we derive a particular class from this geometry, this draw can be given a real implementation. The destructor of the class releases the vertex array object and vertex buffer object on the GPU. One particular type is the parametric surface, which is derived from the general geometry. The parametric surface can be converted to a triangle mesh in a uniform way, so we consider the unit rectangle of the parameter space, define rows and columns of sample points, evaluate the parametric equation of the surface here, and also the derivatives, and compute the normal vector at these sample points, and store the information associated with a vertex in a structure called vertex data. A vertex has a position, it has an associated normal vector, which is just the normal vector of the parametric surface here. It also has an associated texture coordinate for texturing. The generate vertex data function calculates the data members of this structure based on u and v parameters that are assumed to be in the unit interval. The texture coordinate of the vertex will be just a direct copy of the u and v parameters. The position will be just the output of the parametric function, ruv. Note that when we are dealing with the parametric surfaces in general, we do not know yet what the definition is of this parametric surface. We define a pure virtual function called evaluation that gets the UV parameters and computes x, y, z Cartesian coordinates associated with the UV parameters. On this level, this is a pure virtual function. Note that instead of using float types, all parameters are of dual number types, because we need not only the x, y, z Cartesian coordinates of the point, but also the partial derivatives with respect to u and v in order to compute the normal vector, because the normal vector of a parametric surface can be calculated as computing the partial derivative of the surface function with respect to u and v, and then taking the cross product of the two partial derivatives. So to prepare for automatic derivation, we replace normal floats by these dual number types. Returning to the generate vertex data function, we define the yet unknown x, y, z Cartesian coordinates together with the derivatives as dual numbers. U is going to be the first derivation variable. Its value is lowercase u, the input parameter, and it has two derivatives because we have to compute the derivative of the surface evaluation function separately for input variable u and input variable v. Concerning the derivative with respect to u, if we are talking of u, the derivative of u with respect to u is 1, and the derivative of u with respect to v is 0. Similarly, when we are considering v, its value is lowercase v, the input parameter. The derivative with respect to u, the first derivation variable, is 0, and the derivative with respect to v, the second derivation variable, is 1. All other parameters that are independent of the derivation variables must be defined with a dual number which has a value that is equal to the real value of this parameter, and the derivatives with respect to both derivation variables are 0. And recall that this is just the default constructor of the dual numbers. Having x, y, z and u and v, this evaluation function is called, which is yet a pure virtual function. But we assume that from u and v it generates x, y, z, and recall that when we implemented the dual number, f is just the value of the function. So when we obtain x, y, z, taking the f data member, we get the value of the parametric function, so which must be stored in the position. In the dual number representation, d is just the derivative. Let us go back. I am talking of this, so f is the function value and d is the derivative value of a dual number. And d may be an array if we have multivariate functions. So when evaluation returns, x, y, z will have not only the function values but also the derivatives, and taking the first components of the derivatives, we get the derivative with respect to the first derivation variable u, and if we take the second components of derivative d, we obtain the derivative with respect to the second component v. The normal vector is just a cross product of the two partial derivatives. The creation function of a parametric surface can be implemented without knowing the actual implementation of this evaluation function, because generally speaking, creation means the conversion of the parametric surface to a triangle mesh and loading this triangle mesh to the GPU in the form of a vertex buffer object or vertex array object. We use triangle strips because triangle strips are the most optimal way of encoding tessellated parametric surfaces. If we take a unit square and sample it with rows and columns of sample points, a row will correspond to a single triangle strip. If we have n number of rows and m number of columns, a single row will have m plus 1 multiplied by 2 number of points in it. These number of points will belong to a single triangle strip, and we have n rows, which means n number of triangle strips. Data is prepared in this CPU array. The sample points are visited one by one, and using the coding technique of triangle strips, for every sample point we compute u and v parameters associated with this point and call the generate vertex data function to compute the corresponding structure here, representing the position on the surface corresponding to this UV parameter pair, the normal vector, and also the texture coordinate pair. So when this fourth cycle is completed, the data will be encoded in this vertex data array and follow the rules of triangle strips. So this data is copied to the GPU with GL buffer data function. We specify that in input register number 0 of the vertex shader, position information will be copied. In input register number 1, normal vector information will be copied, and in input register number 2, the texture coordinates will be copied. For a particular point, we will copy 3 floats to input register number 0, with the offset that is derived of the offset of data member position in the vertex data structure. Let's go back. It's here. In the vertex data structure, the offset of the position data member is 0. So this is copied to input register number 0. Input register number 1 will get the normal vector, and input register number 2 we'll get the texture coordinates, and for a texture coordinate pair we copy only 2 floats. We can draw it as a collection of triangle strips because every row in our regular grid sampling the unit square is a separate triangle strip. So we visit all rows one by one, and for a single row we render that row of sample points as a single triangle strip. So this is a general parametric surface class. It has a pure virtual function called evaluation. When it comes to a particular parametric surface type, only this evaluation function should be implemented. And we can inherit the generation of information associated with sample points and also the tessellation of the surface into a vertex array object or a triangle strip structure. So our first example is the sphere. In the evaluation function, we have to implement the parametric equation of a sphere, which is pretty straightforward. We use just spherical coordinates. Before using spherical coordinates, we need to realize that in spherical coordinates, the two angles are not in the unit interval, but angle theta, that is in between the North Pole and the South Pole on the Earth, goes from 0 up to pi, and the other angle phi that goes around the equator is in the interval of 0 up to 2 pi. We consider phi as u, the first parameter, but we have to transform the unit interval to an interval of length 2 pi, and we have to multiply v by pi in order to get the range between the North Pole and the South Pole. Having transformed these parameters, we use just the definition of the spherical coordinates and the formulae how to obtain the x, y, z Cartesian coordinates from parameters. Note that here every variable is a dual number, so we just implement the computation of the surface evaluation function, and the derivative computation just happens automatically thanks to the dual number implementation. We don't have to pay attention to the computation of derivatives. The second example is the tracticoid. Tracticoid is a constant negative curvature surface. It also has a simple equation. It is similar to the sphere in the sense that we have to transform u and v parameters from the unit interval to an interval that meets the requirements of tracticoids. When this transformation is done, we just implement the parametric surface equation of tracticoids. Derivative computation is automatically taken care of by the dual numbers. Cylinder is pretty straightforward. There is a circle in a cylinder, can also be imagined as a rotational surface, and in the other direction it has just a linear structure. Torus, we know the torus equations. Möbius strip, Klein bottle, these are getting more complicated, but the basic idea is the same. So we have a parametric equation. We express this parametric equation with dual numbers. So when this function returns the computed values, we have not only the x, y, z Cartesian coordinates of the point, but also the derivatives with respect to the u and v parameters. And the Boy surface, finally a Dini surface. Okay, and now the object that can live in this virtual world. An object needs a shader, which is activated when this object goes through the rendering pipeline. An object has a material, texture. It is defined by a triangle mesh. Already on the GPU, we call it geometry. It has transformation or animation parameters, including the scaling factors along the three coordinate axes, translation, and rotation axis and rotation angle. Note that an object is associated with shaders, materials, textures, and geometries, and an object does not contain them directly. And the reason is that in this way, many objects can share the same shader, material, and texture or geometry, and we do not have to redefine them as many times as objects want to use them. The constructor initializes these parameters. we have a set modeling function that computes the modeling transformation and also the inverse of the transformation matrix. We need the inverse to transform the normal vectors, while points are transformed with modeling transform M. These matrices are computed from the animation parameters, scaling, rotation, and translation. And the modeling transformation first scales the object, then rotates around the rotation axis by rotation angle, and finally applies a translation. M-inv is the inverse of transformation matrix M. Generally, it's not so easy to invert a 4x4 homogeneous linear transformation matrix, but we are lucky here because we represented the transformation matrix by elementary transformations like scaling, rotation, and translation, and these elementary transformations are trivial to invert because of their geometric meaning. If transformation is first scaling, then rotation, and finally translation, its inverse is translating back, then rotating back, and finally scaling back. Translating back means a translation with a negative vector. Rotating back means rotating around the same axis but with a negative angle, and scaling back means scaling with the application of the reciprocals of the scaling factors. The general drawing of an object is here. It gets the rendering state, which already contains the parameters of the light sources and the camera, for example. It first computes the modeling transformation and its inverse with the set modeling transformation function. We have discussed it here. The computed modeling transformation and the inverse are set in the rendering state, and also the MVP model view projection transformation matrix is computed. The material in the rendering state will be the material of this particular object, so is its texture, and we call the shader's bind function to activate the supplied information in uniform variables of that particular shader program. Finally, we call the geometry's draw function to trigger the GPU to send the VAO and its VBOs through the rendering pipeline. A general object also has an animate function which doesn't modify the transformation parameters with a single exception. It makes the rotation angle proportional to the time, so we can expect a rotating object with a constant rotation speed. The virtual world is called the scene. It's a collection of objects. This may be a heterogeneous collection. We need also the camera in the virtual world, and the virtual world also has a set of light sources. In the build function, the virtual world is created. Recall that we need shaders, materials, textures, geometries, and objects as well, while objects can pick from particular geometry, shader, material according to its own taste. So we have discussed three different shaders. We create them. Only one shader of a particular type is enough because objects can share the same shader. So we are going to have a Phong shader, a Gouraud shader or vertex shader, and a non-photorealistic rendering shader. Here we define two materials, diffuse specular materials with different diffuse and specular reflectivities and different shininess parameters. We will have two textures in our collection. Both of them are checkerboard textures. We have just this single texture type, but they are different in the number of rows and columns of the checkerboard. The prepared geometries are the sphere, tracticoid, torus, Möbius strip, line bottle, Boy surface or Dinnis surface. Then the creation of real objects starts. As I said, an object can pick shader, material, texture, and geometry. This first object called sphere object 1 is shaded with a Phong shader. It is defined by material number 0. It uses texture 15 times 20 for the modulating of diffuse and ambient reflectivities, and it has a geometry of the sphere. Additionally, we can immediately set transformation parameters like the translation or the scaling factors, or we rely on the default values as we do it here for the rotation axis and rotation angle. And when the object is really created, we add this particular object to the collection of objects defined here, which is the real definition of the scene. The second object is a tracticoid object, also rendered with the material 0 and texture 15 times 20 and using per pixel shading. Its translation and rotation are set differently, so the two objects will not be at the same place of the virtual world, so we can see them separately. The third object is a torus object. The fourth one is a Möbius strip, then a Klein bottle, Boy's surface, and Diniz surface. All of them are shaded with a Phong shader. So we already created a kind of zoo of different geometries and different objects. Now we triple this zoo and create these objects 2 times with this for loop. But while we are doing that, the transformation parameter is modified just to translate the row of objects to a different place in order to make them distinguishable, replacing the Phong shader in the first round of objects to Garrod shader and also MPR shader. So we can have 3 lines of object collections. The first has all objects with Phong shader, the second renders all objects with Garrod shader, and the third with NPR shader. The camera of the virtual world is set, and we are going to have 3 light sources, and their parameters are initialized. Note that we put all 3 light sources to ideal points, so we are going to have 3 directional light sources. But rendering a virtual world means that the camera parameters and the light sources are written into the rendering state, and then we visit every object one by one and ask the object to draw itself based on the common render state, storing all the information about the light sources and the camera. The animation of the virtual world means that every object should animate itself. The scene is a global variable because it is created in the onInitialization function. It is created here. During creation, we also enable the Z-buffer algorithm and disable backface culling because we cannot guarantee that we always see the front face of an object. The onDisplay is responsible for redrawing the screen. In this case, we set the clear color, clear the frame buffer and also the Z buffer, and then render the scene based on its actual state. This program doesn't react to keyboard events or mouse events, but it does have an implementation of the onIdle function that is responsible for executing discrete time simulation. So what is that? Recall that when some time elapses, the operating system calls our application and informs us that the time elapsed in this onIdle event. But there is no guarantee whatsoever about the maximum time between 2 onIdle calls. If we want to do simulation, it's often disturbing because we want to assume that objects move along a linear path in this small interval, or they didn't get too far away, so it would be enough to check whether they collided only one particular point of that interval. But if the interval can be very large, these assumptions are not valid anymore. To handle this problem, if the time difference between the actual execution of the on-idle and the previous execution of the on-idle called t start is too big, then this time interval is decomposed to small time intervals of length at most dt, and the scene's animate function is called multiple times for these small time steps, and in this way our animation will be valid even if there is a huge gap between two on-idle calls. Let's see how it works. So indeed, this is the zoo of objects. We have 3 lines of the same set of objects. This is a sphere transformed into an ellipsoid. This is a trapezoid, torus, Möbius strip, Klein bottle, Boy surface, Dinnis surface. The first row is rendered with Fonck shading and texture mapping. The second row is rendered with Gouraud shading and without texture mapping, and the third row is rendered with non-photorealistic rendering and also using texture mapping.